Hey guys, this is Mr. Noyes. I'm going to talk about the positive physics that deals with diagonal forces. We already did objects that are on a ramp that was having forces that were diagonal. But these are more cases of it. Okay, so right here, this is his first case. This guy is on a tightrope, I guess, and that's his weight. He happens to be right in the very middle, the midpoint of this tightrope. So both of the angles here are identical because he's right in the middle. And the tension on the left is going to equal the tension on the right. Okay, so our job is just to come up with some equations if we had to find any of these values, TL or TR, given the weight. Okay, so if you look at this picture right here, the two tensions, the left one and the right one, they have identical x components but in the opposite direction, and identical y components in the same direction. And so we can assume that net force is 0, and that therefore the x components cancel out and the y components cancel out. So the x components have to cancel out. So TLX is going to be like negative something, and then TRX is going to be the same value, pointing to the right, positive, they'll cancel out and equal 0. Okay, how about the vertical components? The y component of the tension right here has to be the same as the y component of the tension on the right. So we can say TLY is positive plus TRY. Okay, the positive ones minus the weight would equal 0. Okay, so maybe I should have just said the way I like to do this is just say TLY plus TRY minus the weight is 0, and I don't put negatives on any of these. So I would rewrite this I would just write this as negative weight equals 0, and I wouldn't put the negative on the weight when I plugged it in if I did that. Over here, I would just say TRX minus TRX would equal 0, and then I wouldn't have to put a negative on the left one. When we're doing dynamics equations with a free body diagram, you don't have to put in the negatives if you're using your picture as a reference. Okay, so I can also say the x component would be, if you wanted to find it, that'd be like q times cosine of theta. And TRX would be the tension in the right half of the cord times cosine of theta. These would be identical. Theta being the angle from the horizontal that the rope is bent. And then TLY would be TL sine of theta, and TL I'm sorry, TRY would be TR sine of theta. So if we had numbers, we could figure all this out. Okay, now let's do it. Okay, so here's a positive physics one. Well, if you're hanging there, if you're just hanging at rest, F net, which I show is that, sigma F, F net is 0. Find the angle right here. Okay, well, just looking at this picture, the tension in the rope right there, can be broken down in X and Y components. So, let's see. So, let's say if F net is 0, then F net X is 0. So we can say, I don't know, I'll call this T2. So this is T2Y. And this is T2X. And let's call this T3. T1. Okay, so we got 2 ropes. Okay, so back to F net X. We know that Tx minus T, which is this guy, right? T1 is equal to 0 because they have to, the X components have to cancel out. Okay, so that's, again, that's T2 X. This arrow right here is T2Y. And this guy, the resultant of the 2 is T2. That's the tension in the rope. Okay, so TX1 so I'm doing the X component, sorry. So T, let's clarify this. So T2X is positive, and then minus, because he's going the opposite direction, T1 is 0. So I can find T2X because T1's given. So T2X minus 400 equals 0. So T2X equals 400. Now you can do a trick right here to find what the angle is. By the way, if you had to find T2Y minus, because it's going the opposite way, the W, the weight, is equal to 0 because sigma F in the Y direction is also 0. Okay, so the weight is 700. So T2Y is equal to 700. Okay, now, if I were to ask you to find T2, that's Pythagorean theorem because you got the X and Y components. T2Y squared plus T2X squared. I'm just using Pythagorean theorem with this triangle right here. I'm moving a T2Y over to the opposite side. So T2 is equal to 700 squared plus 400 squared. And so that equals, calculate it out, 806 newtons. Now, they ask for the angle right there, that angle. So you can use your equation sheet, inverse tangent of the opposite, ty over tx. Actually, that's t2. Okay, so that's on your equation sheet with the q. So inverse tangent of 700 over 400. And that comes out to be 60.3. Okay, here's a similar problem from positive physics. It says a helicopter. The helicopter is neither gaining nor losing altitude, so it's just basically in the y direction. The net force in the y direction will be 0. That means, okay, the thrust is provided by the rotors here, and so is straight up relative to the helicopter, but really it's slanted from our point of view. Okay, so I don't know what that angle of slant is. It would be the same as this angle. No, it wouldn't be. Okay, so we don't know what that angle of slant is. Let me erase it. Okay, so there's x and y component to a slanted force. We got THX. TH means thrust. And THY. Okay, find the thrust. So we're supposed to find that.
The National Weather Service has issued a flash flood warning.
Okay, we're supposed to find that middle finger, the 3-finger rule, the slanted force. Okay, but the speed is constant. They hide that there. So we can say the net force in the x direction is 0 as well. So let's do this. Sum of the net force in the y direction is 0. That equals THY minus the weight. So 0 equals, right here, I don't know what THY is, minus 70,000. So THY, the y component of the thrust, is 70,000 newtons. I can do the same thing with the x components. Sum of x components equals 0 because it's going constant speed. So the sum of EFX is equal to the x component of the thrust minus the drag. Okay? So we're looking at these two forces right here. Okay, so 0 equals THX, x component of the thrust, minus 5,000 newtons of drag. So THX equals 5,000 newtons. Okay, so how do you find the resultant given the x, y components? You should be able to do this. So the thrust is equal to the sum of the squares of the components, of its components. So that would be 70,000 squared plus 5,000 squared. Square root of that. So I'm getting 70,000 178 newtons for the thrust. Now I want the angle of the bank. Okay. Okay, this is kind of weird. So this angle right here is not this angle right here. Give me a different color. Okay, so this angle right here is actually this angle right here. So that's really what I'm looking for, the bank angle of the helicopter. So, so I'm gonna have to do some trick. I can find this angle theta, and then I can subtract it from 90 to find the bank angle right there. Again, the bank angle is the angle up here. Okay, so find that angle theta, then subtract from 90. Okay, it'd be THY or THX. That's over partners. Over the X component. So that'd be 70,000 over 5,000. I'm getting that angle to be 85.9 degrees. So we just found this angle right here, but this angle is a complement of it. So I gotta subtract that from 90. So the bank angle, that'd be of the helicopter to the horizontal. I don't know what you want to call that. That angle, here's the helicopter. Boy. Anyway. The bank angle would be 90 minus that. So, 90 minus 85.9 is equal to what? 4.1 degrees, right? Yeah, so that's the bank angle. Okay, finally,